Hello and welcome back to Hands-on Problem Solving with Machine Learning, and we're talking about a new chapter on predicting the future. And let's talk about in this video building a robust model with cross-validation. So I'm back in my Jupyter Notebook environment, an excellent tool for any data scientist to really try things out and really rapidly iterate on new models. It's also quite good for presenting data science work, as you can see from this series of videos. In fact, it's one of my favorite and easiest data science tools to use. And so in this section, we're going to talk about predicting the future, and it's really about the problems of when your model performs remarkably well or quite well, or you've generated some sort of performance, right? Like you're done some work and it's working, and it works quite well on your existing data sets, on the data points you have. But for some reason, when you put it in production and you try to test it in real life, rubber meets the road and it fails miserably when it sees new data, right? So it doesn't really perform when it sees new data. Everything that you've seen while you're training it on your own data set doesn't seem to hold when it comes to the new data. And so in this chapter, this is really about how we can build models that are robust, that could accurately predict future data points coming in, and not just learn the features of our own current data sets, or even worse, remember the data points in our data sets and are simply memorizing things and not really generalizing into future new data points. And so you really don't want that, right? As a data scientist, you're given some data, you're supposed to create a data model that generalizes into the future. And so you really need to do that to become a successful data scientist. So let's look at three big pillars of how we can make this better for us, right? So how we can use different techniques in data science to make this better. So the first thing we can do is cross-validation. And so in this particular video, we're going to focus on how we can build robust models that predict actually the future and not just remember all the stuff that has been fed to it with cross-validation. And so the first sort of mini example is really using the train test split function to do sort of like a mini cross-validation. To do this, we're first importing in in7 numpy as np, and then we are looking from scikit-learn.model-selection, importing the train test split function. We're importing some data sets from scikit-learn, and we're importing the linear model, right? So in the last line of in7, we are loading Irish into the dataset variable. So that's in7. So in in4, what we're really doing is we are trying to look at the shape or the number of rows and columns that the dataset has on the data side. So on the input side, or even like the design matrix, you want to get into it. And so this dataset has the data of the dataset, the input part of the dataset has 150 rows and 4 columns. And if we look at the target side, the output side, the label side, we have 150 labels. That gives us the correct answer or the correct label of the 150 data points that we see in out4. So the very first baby step that we can do is in in6, we're deciding how much of the data set to hold out as a testing set, and we define this holdout percentage at 40%. And so converting this percentage into a floating point number gives us 0.4, and we're saving this holdout percent in the holdout percent variable. And so to not overfit the entire data set, we want to split the data using the train test splits function. And we feed in the dataset's data part and the dataset's target part into train test splits, and we tell that the function that the test size is the holdout percentage, which is 0.4. And also we fit in the random state parameter at 42, which allows us to reproduce this train test split effectively later on. And so if we inspect the shapes of X test, Y train, and Y test, we can see that our 150 data points has been segmented into 90 and 60 data points respectively, and we can see that the number of columns remain intact, which is exactly what we want. So in N27, what's happening here is we're creating a new model, right? And this is a logistic regression model with an L2 penalty, with a primo formulation, with 0.0001 tolerance and a C value of 1. So what's the reason why I'm showing you this is because typically what happens is you create a new model like you do in N27 and you fit it on your training data. And then you look at the test sets of how this model performs, and then you just tweak the inputting parameters or the hyperparameters of this logistic regression model, and you basically tweak it until your model learns the right things from the training sets, which allows you to perform well in the test sets. So then it's A, messy, and B, you're basically leaking information from the testing sets into the training sets. So a more superior way to do this is to use k-fold cross-validation, right? So the idea behind cross-validation is very simple. What if we perform k times this train test splits at random? So we always split at 10% or 30%, and we do it 5 times randomly. And of this 5 times, we then try to fit different logistic models on it and with different parameters, and we see which one wins, right? So here we are importing the cross-validation score of the scikit-learn model selection module. And so what this does is, again, we create a model, a logistic regression model that has a penalty of L2 and a primo formulation. And this model basically is then fitted on the cross-validation score, and the cross-validation basically splits the data 5 times randomly and fits the model to see what the model is, how the model is performing across the 5 splits, and we'll pick the one that wins, right? So for example, here we can see that the scores are 1, 0.967, 0.33, 0.9, and 1 respectively. So depending on how you split the data, the model performs differently. And so what we can do is create and compute the 95% confidence interval of the accuracy. And so we can see that the mean score is 0.96, and the standard deviation of the score is 0.07, right? So not too bad, but not amazing. And on top of this, we can also use a custom scorer instead of model.score. So for example, if we want to score using the F1 macro scoring mechanism, which is arguably better for a classification problem like the iris datasets, then what we can do is use the cross-validation score, again, feed in the model, the data, the target, specify that we want 5 cross-validations, and we specify the scoring as f1.macro, which allows us to realize a completely different array of scores that allow us to have a better picture of what the scores should be.